Right, good evening everybody. And thank you all for coming to this evening event, which is actually a multi-header in the sense that this is our certainly Mark Blacksell Geography Lecture, which is also serving as one of the Royal Geographical Society RGS regional lectures, and it's also serving as the annual Southwest Quaternary Lecture. So there are very few people who could possibly cover all three of those, but actually our speaker today quite genuinely does in Professor Jamie Woodward. Jamie is a highly respected quaternarist. He's also head of geography at Manchester University, so he hits the book geography book. And what's more, he actually knew personally and was a colleague early in his career of Mark Blacksell, because Jamie, having done his first degree at Aberystwyth, then gone to Cambridge, which was, in some ways still is, a hotbed of quaternary science, then had a postdoctoral position at Exeter, and I'm delighted to welcome colleagues from Exeter here this evening. So he knows this part of the world, knows Exeter well. Before moving to lecturing positions in Manchester, Leeds, and then back in Manchester again. Now, Jamie's work has involved studying the past, but also the present, in particular in rivers, with an interest also in where we would start in the mountains, where there are now, or have in the past, been glaciers. So he's worked closely with colleagues working on glacial history, but he's also worked at the bottom end with colleagues interested in human history, in particularly through the archaeology of areas, including the Nile, but also elsewhere in that region, particularly in the Mediterranean. He's author of a rather fine little book which came out a year or two ago. We have a copy here dedicated to Neil from Jamie. You may well know these.
I didn't dedicate the book to Neil.
I hope I get away. A very short introduction to, you will know these books, very short introduction to, this one is to the Ice Age. And it's a very interesting read indeed, and I was delighted and fascinated to learn things I didn't know about the 19th century, and Jamie has a side interest in the history of science, and Ice Age science in particular. He's also edited now 3 books, effectively, on the Mediterranean, one on rivers, another on physical geography, both very fine books. I can say that since I have chapters in both of them, and most recently one on glaciers in the Mediterranean. But one of Jamie's key research areas has taken him further south from the Mediterranean to the source of the biggest river that flows into that sea, the River Nile. And over more than 20 years he's been working with teams from the British Museum and elsewhere on the archaeology of the River Nile Valley, particularly in its middle reaches in the Sudan. So we're really delighted today to have a chance to listen to the quaternary history of the River Nile from Jamie Woodward. Right.
Thank you, Neil. Thank you very much indeed. So from a very short introduction to a very full introduction, delighted to be here. Thank you very much for asking me to talk this evening, and particularly delighted to give the Mark Blacksell Public Lecture, because Mark was a colleague of mine at Exeter when I was a postdoc there between 1990 and 1993. I think everybody will agree that was the golden years in Exeter. And Mark was a good friend and a very good colleague, so I'm delighted to be able to do that this evening. My talk's in roughly 4 parts. What I'd like to do is give you a little bit of background about quaternary environmental change in the Sahara and in the Desert Nile. From a quaternary perspective, I'm not going to do the entire quaternary, we don't have time. And then I'm going to focus in on the Holocene and look at 2 archaeological projects that I've been involved in on and off over the last 20 years or so. I think that addresses the geography, the human geography, the cultural record. And then talk about some more recent work we've been doing on sediment sources to try and understand how the Nile has behaved over the last sort of 8,000 years or so. Now, how many of you have been to Egypt? You've seen the Nile. Okay. How many of you have been to Sudan? Okay, there's always a little trickle, so there's a few intrepid people, that's good. We're interested to speak to you afterwards. Now, lots of people have contributed to the work that I'm going to be talking about this evening, archaeologists, geoscientists, etc. But all the field work that I've done, the geomorphology, the sedimentology, has been done in collaboration with this young man here, Mark Macklin, now at the University of Lincoln. So that's an acknowledgement for the geomorphology. Now, you may know that Sudan is on Donald Trump's list of 7 states where people can't travel to the USA. I just want to put on the record, it's been one of the privileges of my career to spend 20 years working in Sudan with the people of Sudan, particularly in the north of the country where we've been shown great kindness and great generosity and interacted over many years with the locals, with the farmers and with other people in that part of the world. But what I want to share with you today is some of the fantastic landscapes in that part of the world and some of the stunning sedimentary records that record long-term changes in the behaviour of the Nile, and also the societies who lived alongside the Nile over that time period. So one of the things that I'm particularly interested in is how rivers respond to environmental change. Okay? And the River Nile is a particularly good place to consider how a river system responds to global climate change. Because if you consider the hydrology of the Nile, this is the former Sudan before it was split into 2. It's literally plumbed into 2 main components of the global climate system: the summer monsoon in the northern hemisphere, and then equatorial rainfall down from the tropical regions of the intertropical convergence, so down in the lakes region of Lake Victoria. So this gives us the iconic, probably the most famous flood peak anywhere, the famous Nile flood. This 100 days of inundation stretches through primarily through August and September. Now, a key characteristic of the hydrology of the Nile are its marked spatial and temporal variability. So we have this classic flood peak here, but that's dominated by flows from the Blue Nile and also from the Accra to the north. And that's dominated by the summer monsoon. It's a very strong seasonal hydrological signal. Then from the south, we have the White Nile, when you could call that the base flow, if you like. That maintains flows in the main Nile throughout the year, but it's overwhelmingly dominated by the Blue Nile, and to a lesser extent the Accra during the summer floods. Now, what I'm particularly interested in is we've been working in what you might call the Desert Nile. So this is Khartoum here, where you have the confluence of the Blue Nile and the White Nile. And we've been working here near Dongola and in northern Sudan here between the 4th and the 2nd cataracts. And I published this map a couple of years ago, and I think this characterises for the first time the Desert Nile. This is the catchment downstream of Khartoum and Accra, which now doesn't have any perennial streams. There's the occasional flash flood, the occasional ephemeral flow, but it has a catchment area over 1 million square kilometres. And what I want to show you today is show you the significance of that part of the Nile system. And today it doesn't contribute any water or sediment that's measurable to the main Nile, but in the past it contributed a significant component of the sediment and the water load of the Nile. And I'll show you some evidence to demonstrate that. What you need to remember, first of all, is the Blue Nile here. It's only 10% of the entire catchment area. The Blue Nile is the motor that drives the Nile. Most of the sediments and most of the water comes down the Blue Nile system. The discharge of the Nile is fairly modest for such a big river, but about 30% comes down the White Nile, 70% down the Accra and the Blue Nile. If we look at suspended sediments, it's even more spatially marked. Relatively small amounts from the White Nile, often less than 3%. The sediment flux, the classic dark alluvial silts of Egypt and Sudan, are dominated by volcanic material that comes down the Blue Nile from the Ethiopian highlands. It's a very distinctive sediment source. So we've got marked contrasts in the spatial and the temporal variability of water and sediment. So the White Nile here is by far the largest catchment. That drains right down into the lakes area in the equatorial regions of Lake Victoria, Lake Edmund, Lake Albert. And the Blue Nile and the Accra, they drain the steep, very seasonal, young volcanic Ethiopian highlands with very high sediment yields. And then they converge at Khartoum and then follow the 2,500 kilometre journey down to the Mediterranean Sea. So remember, there's 2 components to the global climate system, and so the Nile is a good place to investigate some of those, how those changes in the global climate impacts on river behaviour. Now, if you were to take a long sediment core from the eastern Mediterranean here, off the Nile cone, this is looking at the long Quaternary record, you would find these very distinctive dark horizons. These are known as sapropels. That's a beautiful contraction of Greek words, sapros and pelos, which basically means smelly mud. Okay? So these very dark, distinctive organic horizons, which have organic contents in excess of 10 to 20% occasionally, they're very distinctive, and they appear in cycles down these long sediment cores. Now they're dark, they're organic-rich mud layers found characteristic of the eastern Mediterranean. Now they represent periods when the Nile flow was much greater. And there's been much debate about how they formed, but in the eastern Mediterranean, many of these deep basins, what happened is during these sapropel periods is there's increased flows from the River Nile. It stratified the water column and prevented mixing, so there was the bottom waters became anaerobic, okay, they became anoxic, and the organic material doesn't break down. So these sapropels periodically build up on the floor of the eastern Mediterranean. And there's been a lot of debate how they formed. In the 70s, some people suggested they were related to glacial cycles, they were related to glacial meltwater coming down through Europe, through the Black Sea and the Aegean. But the big breakthrough was this famous paper in Nature by a group of French workers led by Martine Rossignol-Strick, this wonderful title, After the Deluge. She related to these sapropels were a product of increased rainfall in the tropical regions. So the Mediterranean provided a long-term record of changes in Nile flows, a more intense monsoon. Now these changes are driven by one of the Milankovic cycles, and it's precession. Now, precession, without spending too much time on this, there are three components of the Milankovic cycles which influence climate. It's related to the geometry and relationship between the Earth and the Sun. And precession has a cyclicity of between 19 and 23,000 years. So basically, the axis of the Earth's rotation wobbles. And the analogy that's often used is a spinning top slowing down that starts to wobble. It's a very good analogy. And basically what that means is we get changes in the amount of solar radiation received in the tropical latitudes. And this curve here shows the amount of insolation, the amount of solar energy at 30 degrees north in the northern hemisphere. And there's this very marked cycle. Now what's interesting here is when dune insolation is high, we tend to get sapropels in the eastern Mediterranean. So we tend to get more water coming down the Nile and a more intense monsoon. And so for these sapropel records, which are numbered from youngest here, going back right back through the Quaternary and into the Miocene, Pliocene and the Miocene, sapropel 1, sapropel 2, sapropel 3, and so on. Now I want to focus in a little while on the time period associated with sapropel 1. This formed in the end of the last glacial period into the early Holocene up to about 5,000 years ago. And this was a period of profound environmental change in the Nile Valley and in the Sahara. So, also what's interesting about these sapropels is they often have very abrupt stratigraphic boundaries. They tend to begin and end very quickly. These cycles take a long period of time, but there must be feedbacks in the system where the system trips and the sapropels start to form relatively abruptly and then they end abruptly. And there's been much debate here about this last sapropel, about the timing of ending and what the climatic conditions were associated with that, and what that means for the behaviour of the Nile. So these, I showed you the flood peak of the modern Nile. We've got long-term changes here in the behaviour of the Nile going right back into the Miocene. And this precession cycle is controlled by the gravitational pull of the moon and the sun. So it's quite a wonderful thought to think that the gravitational pull of the sun and the moon change the discharge of the Nile in the long term. It creates a more intense monsoon and then a weaker monsoon. We see that in the volume of water coming down the system. And I'll come back to that. Okay, let's think about the Sahara and this part of the world for a bit of context. So the Quaternary period, the last 2.5 million years, has seen key changes in the African monsoon. It's been periodically strengthened, it's been more intense, and it's also been extended. So this green tropical belt is extended much further to the north. And in the early Middle Holocene, at the time when we get sapropel 1 forming in the Mediterranean, between 11,000 5,000 years ago approximately, we see both an amplification and an extension. And this produced what has been known as the Green Sahara. So the Sahara Desert as we know it now did not exist. Okay, it was a very different environment, very different landscape. So during the Green Sahara, this region received high amounts of rainfall, 500, 600 millimetres of rainfall, supporting diverse vegetation, permanent lakes, human populations, and permanently flowing streams. And the evidence for that comes from archaeological evidence of paintings. There are lake sediments, there are pollen records that record this humid interval. And the early Holocene interval is one in a long succession of wet phases that extend back over an extended period of time. So, these were paced by orbital precession, and it extends back to the late Miocene. What's the mechanism? How does this work? Well, current understanding is when the precessional cycle approaches perihelion during Northern Hemisphere summer. At the moment, perihelion, the Earth is closer to the Sun in the Northern Hemisphere in January. 11,000 years ago, it was in July, and that created more solar radiation, greater insulation in the Northern Hemisphere. So this drives a much stronger gradient, the continents warm up, this brings moisture off the oceans, and it strengthens the monsoon, bringing rainfall deep into what is now the Sahara. So there's a great extension of this green belt. This should go green now. Did that work? And the Sahara as we know it now no longer existed. So during the Quaternary, this was a very, very profound environmental change. Just as profound as the glaciations that we're more familiar with in more northerly latitudes. It was a very profound environmental change. It had major implications for the archaeology and the ecology of this part of the world. Okay, let's go to the Nile and think about some of the records. The Nile traverses the largest hot desert on Earth. It straddles 35 degrees of latitude. It's the only river that does that, from the equator to the Mediterranean. And we're going to be focusing on the Desert Nile, the present Desert Nile, Khartoum to Cairo. We're focusing on the records from northern Sudan. I want to think about what does this fluvial record look like. There's been a lot of work on lake sediments, a lot of work on the archaeology in this part of the world, but relatively little work on the fluvial records. So I want to show you some of the landforms and the sediments that record environmental change in the Nile Valley. And then think about what it can tell us more generally about policy and environmental change in this part of the world. Now, whenever I tell somebody I'm working in Sudan, they ask me why, okay? And there are a variety of reasons why Sudan is a good place to do this kind of research. It's a very different river from the Nile in Egypt. If you look at the Nile in Egypt, this is Aswan here, the first cataract. This is Lake Nasser and Lake Nubia. Down here, the Nile, down to the Mediterranean Sea. It's a big, long alluvial reach, and it's basically ploughed from Aswan to the Mediterranean Sea. There's been a huge amount of development on the valley floor. Everything's either under the plough, or it's under tarmac, or it's been urbanised in some areas. There's been a lot of development. Whereas in Sudan, the development hasn't happened to the same extent. So we have much better preservation of landforms and archaeology on the valley floor. Secondly, political reasons, it's very, very difficult to export samples from Egypt for political reasons. So we can't take samples out of the country to get them dated. So there's a lot of work on the alluvial records in Egypt, but they're very poorly dated. The best records that we have that are dated, which allow us to relate the river records to the climate records, come from Sudan. And also the British Museum has got a number of live projects that we've collaborated with in Sudan over a number of years. So there's a variety of reasons why it's a good place to work to do this kind of research. One of the things that's interesting and exciting is exploring interactions between the desert and the river. This is the Nile in northern Sudan, rising in the summer flood in July, late July, early August. These are dunes on the west bank. You get wonderful interactions between the fluvial system and the desert dune system. And you get very distinctive grey Ethiopian silts intercalated with orange sands. So those sediment sources are very distinctive, and we'll look at some of those interactions in more detail a little bit later. Now, one of the things we're especially interested in is also looking at evidence for environmental change over the last 5,000 years or so. There's been an assumption that once the Sahara went arid, that everybody converged on the Nile Valley, rise of urban civilization, etc., and it was pretty hot and dry up to the present day. But we also see evidence for quite marked climatic changes even in the last 5,000 years, and I want to show you some of the evidence for that. This is an aerial photograph I took in 2008 in northern Sudan, flying to the north. Many of you will spot it. There's a beautiful paleo channel here now. This is in January, so the Nile's at low flow. So we call that a paleo channel, an ancient channel. The question is then, so when did that channel dry out? Why did it dry out? Was it a result of a fall in discharge, or did the river just change location? So these are some of the things that we're trying to establish. Now, I've marked the channel here. Let's think that in the Green Sahara, in the early Holocene, when the monsoon was more intense, all these channels are flowing. I can show you evidence for that. We've got more water coming down the Nile. Then periodically, we get these what we call anabranches, parts of the channel systems, they dry out. And we've called this a channel network contraction. So we might go from 3 to 2 or from 2 to 1. And we've got evidence that shows that these are related to major or abrupt climate changes, which results to falls in discharge and a less intense monsoon. I'll show you some of the evidence for that later. There's other types of contractions we get. If we just get a fall in discharge and the channel's narrow, it's another style of contraction. I'll show you some evidence for that as well. So, just think more generally, why do rivers change their form? Why do rivers see falls in discharge? These are some general questions that we might be interested in. There's a big debate at the moment in fluvial geomorphology about whether we can see a climate signal in the fluvial archive. Some American workers have suggested that the climate records are shredded. Rivers are big, noisy systems, and they don't preserve accurate records of climate change. We can think about that a bit more later. There's also an issue here of external versus internal control. So there may be a climate control influencing what this channel is doing and how much water is coming down it, or it may just be that this channel system has filled up with sediment and the channel's switched, or we call it an avulsion, and decided to flow on this side of the valley floor. So that would be an internal control which has nothing to do at all with climate. So we have to try and see if we can work out what's going on within the system. So how do big rivers respond to abrupt climate changes? It's an interesting issue. Also, we want to think about where are the best records of change. Where should we look in the landscape to find evidence of these changes? Can we date them? And then also want to explore how can we then integrate some of the archaeological and the geoscience data sets that I want to present to you. And then think more generally, what can we learn from the Nile? Are there any lessons from these records that have wider relevance? So a little bit of background. Mark Blacksell and I first went out into the Nile, into Sudan in 95 and then back again in 97. Then we had a large hiatus. We were working with 2 British museum projects, first of all in northern Dongola Reach here, and then more recently in Amara West, further to the north. But in the late 90s, the Sudanese government, funded by the Chinese, built a huge dam here at Merowe, which is the biggest water project in Africa at the time. So all the archaeologists in northern Sudan went out here to the third, the fourth cataract to do a huge rescue project. So that diverted them for the best part of a decade. And then in the mid to late 80s, we got some money from the Leverhulme and Australian Research Council with Martin Williams and others. And we went back to Sudan as the archaeologists moved back to the Dongola Reach. And we did a whole series of field seasons there in Dongola Reach and then later at Amara West. And it's the later stage of the project that I want to present some of those new data today. We've written this up and we published this fairly recently. Interestingly, there's plans for more dams here, so all this archaeological work that's going on is often in the shadow of an impending inundation. This is a moving target. The British Museum spent time working out what it would cost to move temples as a result of inundations, but these are plans for dams which haven't happened yet. Okay, let's have a little bit of a look at the archaeology at a big scale. So this is a wonderful set of maps produced by Cooper and Kropolin in Science just about a decade ago. And they show the northeast Africa here in the Nile Valley at the end of the last cold stage, about 10,500 years ago, just in the very early Holocene. The climate was very dry and dusty. All the archaeological sites are focused on the Nile Valley here. But in what's called the African humid period, in this period when we had the sapropel forming in the eastern Mediterranean, this area was much wetter, got the same sort of rainfall as East Anglia at the present time, with 400, 500 millimetres, and we've got lots of archaeology, lots of people out here in the desert. But at the end of the African humid period here, we get the creation and the re-establishment of the desert Nile. There's a lot of archaeology then focused on the Nile, and the desert becomes rapidly depopulated, apart from a few archaeological sites associated with the oases and the water sources. And then, as we go further south, the Sudan is still wet at this time, but the There's got the retreat of the intertropical convergence zone, and this becomes progressively drier. This is where we're working here in northern Sudan. We're interested in what the impacts were on the fluvial system, the waters and the environment in this part of the world. You'll notice here there's just a single archaeological site. That's a site called Kerma, famous Bronze Age civilization. There's evidence of occupation right back into the Neolithic period. This is actually about 5,500 years ago. So I want to spend some time here showing you the records in that part of the world. This is Kerma here, which had a single site. All the red dots on here are Kerma sites. We'll come back to that later. What I want to start off is go to Amara West. This is one of the few places where the Nile takes a right turn and flows from west to east and aligns itself to the northern winds here. And there's around about 1500 BC, Egypt invaded northern Sudan, in the land that they called Kush. It invaded Nubia, it conquered the whole of the region. It built towns. It built the town of Amara West, it built towns at Tombos and Kawa. These were New Kingdom towns, as this area was colonised by Egypt and came under Egyptian control. And one of the famous towns is known as Amara West. And this is a New Kingdom town founded around about that time. And this is where we've been working most recently. This is a wonderful photo I had at the beginning. It was taken with a kite camera. This is Amara West. This is the town that's been excavated very recently. This is the Nile flowing towards us from the west. This is the north here. There's a big ramp of dunes here. This is an island with an anabranch around the outside. This is a Netter Island where we live. We take a little boat trip down here. This is where the excavations are. Now what you have to imagine is a channel system flowing around this town. A nice blue channel coming around here, so that this area was as green as this island, and these sand dunes didn't exist. So the environment of Amara West was rather different in the past. It was founded in the reign of Seti I. He was the father of Ramses II, okay? And it was an important administrative centre. It was basically the residence of the deputy of Kush. So this was Egypt colonising and putting in administration in Nubia after the colonisation of the area. The town was founded on an island with a narrow channel to the north wrapping around here. We're going to run a cross-section. These are the dunes. This is the town of Amara West. We put some water in the channel. It's now dry. This is what the channel looks like. There's a series of cemeteries here with evidence of small pyramids. There's a temple here that faced the channel. It's the classic Egyptian association with a temple facing the river. Cemeteries on the other side, on the opposite bank. This is what Amara West looks like today. Note the amazing contrast between the north and the west of the river channel here, which is dominated by windblown sands, and here to the south and the east, dominated by wadi systems, relatively free of windblown sand. So living this side of the river is good, the other side of the river is not so good. So Amara West there being located doesn't really make sense. There's occupation here on the Netter Island, occupation on Sai Island, that's the biggest island in the Nile, and the modern town of Abri here fringes this meander on this side of the river. This is Neil Spencer, the keeper of Egyptian antiquities at the British Museum, who leads the projects. This is looking to the north. This is the channel we're talking about. This is the Amara West Pallet Channel, which is now dry. And then in the distance beyond this ridge, there's another much bigger channel, which is also now dry. So this site was excavated in the 1920s and the 1930s, and the assumption was the channel dried out after a couple of hundred years, and then the town was abandoned. Okay, so we were testing some ideas about what Neil wants to know is when did that channel dry out? How quickly did it dry out? This is some of the archaeology. It's a wonderfully rich site. Neil runs a blog on the British Museum. It's an urban town with a big wall and a temple and a whole series of houses and alleyways. Fascinating archaeology. Interestingly, the later architecture in the town shows evidence of blocking doorways to stop blown sand coming into the town. So, in terms of chronology, 1450 BC, Pharaonic Egypt conquers northern Sudan or Upper Nubia. Amara West was founded between 306 and 290 BC. We've got good archaeological dated evidence for that. And then Egypt retreated from Kush in about 1110, 1070 BC, and the final occupation of Amara West. And then we've got evidence of occupation of some of the cemeteries rather later. But here we've got a window of about 240, 250 years for the lifetime of this town. Now, Andrew Nicholas is here, so we've put some inundation models. If you just run an inundation model here, just using the topography, we've run through here the biggest flood monitored in this part of the Nile in the 20th century. and it looks something like this. So this is ignoring the dunes and just putting water in the landscape. This is the big channel to the north. This is Amara West here with a little channel running round it. So when that town was founded, it was founded on a small island, which was in between, just upstream of a much larger island, larger than a Netta island, with a major Anna branch here to the north and a major Nile channel here to the south. Strategically, an important location. When that channel dries out, we get what we call a contraction. The desert then comes all the way to the modern Nile. So Amara West is no longer a viable settlement. It's not viable for agriculture. It's a very difficult environment to live in. So what do these contractions look like? We've done geophysical surveys across this channel, and these are some of the reflections that you see here. So when the channel was at its most active, it was about 70 metres wide, and then it contracted to just 30 metres wide, and it periodically filled in with blown sand. So this is a channel contraction. This is what the sediment deposits look like. These are spectacular. So these are coming from the north. When the channel dries out, it fills up with wind-blown sand. Then periodically you get a really big flood that comes down the Nile, reoccupies that channel, maybe excavates part of the channel, but it never has the competence to fully clear it out again. And it progressively, the north bank moves this way in a southerly direction, creating this north channel. So this is the sedimentary record of a dying channel. It's been overtaken by the desert. The Palea channel is filling up, and it's no longer a perennial channel, it's an ephemeral channel. So it becomes narrower and shallower over time. And can you see the blue here? That's when the channel was at its largest extent, and that's when it was at its smallest extent. So the challenge for us, we've identified a contraction that was trying to date it. The interesting thing is, when did that happen? How quickly did that happen? Okay, and that's of major importance for understanding the archaeological record and for identifying the climate signal. So we dig pits in the middle of those channels to look at the sedimentary fill to see if we can identify the last time water came down that channel. This is a beautiful round hole that we dug in the middle of the Amara West channel here. So I'll show you some of the sedimentary records, show you some of the fills, and show you how we date them. So you get down the hole and you look at the sediments and you describe them and you think about what might have been going on. And you may notice here there's some dark layers. There's one here, there's one here, there's one here. There's a series of floods here stacked one above the other. And when you log this section, it's about 3.5 metres deep. What seems to be happening here is periodically, when you get really big floods on the Nile, they breach that barrier of dunes and they reoccupy the channel. But what we see is they do it under very low energy conditions. We're not talking about a flash flood. The Nile rises very, very slowly in the summertime and it falls very slowly. But periodically, these channels were reoccupied. So if you imagine, what does the sedimentology look like? Let's look at flood unit D. We've got a stack of flood units here. Now this is the most exciting sedimentology you will ever see. Okay? I guarantee. This is flood unit D. So we've got Ethiopian silts here, dark grey volcanic Ethiopian silts, sandwiched between Libyan or Egyptian sands. It's enough to make Donald Trump go mad. Okay? All preserved in northern Sudan. Now we know these are low energy because you imagine water comes down the channel, it's full of orange windblown sand, so it reworks some of that sand, so the windblown sand becomes river sand, so you get fluvial structures, but it's all done under very low energy conditions. And then the sediment, suspended sediment settles out. So each of these flood units is capped with a thickness of a few centimetres of fine-grained silts and clays, suspended load of the main Nile. And then a couple of hundred years later, well, it's buried immediately with windblown sand very quickly, but a few hundred years later we get another big flood which comes down the channel. And these flood units have dried and cracked in the sun before they were buried, and the next flood, these are called what we call, well, ripple clasts seems too severe to sound. These have been gently caressed by the water, and these little silt blocks have been uplifted. These are only a centimetre across. They've been uplifted and frozen in time. They've only moved a few millimetres, so it's very low energy conditions. So we can be confident there isn't any scour. We've got a full set of floods here. So for about a 1,000-year period, we've got the record of the 6 biggest floods on the Nile at this time that reoccupied this channel system. And we can date them by a technique called luminescence dating, which allows us to date the sands directly. We've got 3 dates here. This date's interesting at the bottom, 1270 BC, very close to the founding of the town. We know the channel was dry at that point, and we hadn't bottomed out the channel. So we've got a stacked record of Nile, big Nile floods in a Palea channel. Here they have a recurrence interval of about 160 years. We're confident we've got a complete record. excellent preservation. That channel was dry, if you believe the dates, at 1270 BC, and there's another flood unit below there, so it was potentially even earlier than that. So this is showing interaction between the big floods probably breaching the dunes, reoccupying those channels, and then we get a sedimentary signature of those big floods. But what we haven't done, we didn't get deep enough in that pit for health and safety reasons. We didn't get down to the permanent perennial channel of the New Kingdom channel when it was flowing. So I haven't got time to tell you the story, but we got a big excavator here in 2013, and we dug a big trench just near the side of the town. And what this shows us, this is the channel bed of the New Kingdom River, when it was perennial, when it was permanent. And it's got lots of archaeology on here because everyone threw all the rubbish into the river. We were able to date this. Mark Macklin's in a hole here, not for the first time, holding a ladder. And we've got radiocarbon dates on charcoal, which again show the channel was dry 1260, 1210, then an old date here right in the bottom of the channel, 1380. So they're really interesting dates. If we plot those dates on our timeline here, that's the luminescence date from the round pit, these are the radiocarbon dates. If we take those two dates as real, that suggests the channel dried out within a generation of the founding of the town. So for 200 years, people were struggling living in that town when it's been taken over by the desert. And that demanded then a radical rethinking of the archaeological objectives. Because the archaeologists then, looking at the architecture, looking at the archaeology, were then thinking about what is the archaeology of the town battling in an arid environment, thinking about resilience, thinking about sustainability in the context of a town that's been overrun by the desert, dominated by the desert. You see architecture, the doorways in the north being blocked up, doorways moving to the other side of the town, and we've got evidence of floors in the town filling up with windblown sand. So it's a very interesting new take on the archaeology, but that channel could have dried up very quickly. So basically, it wasn't a very good choice to build a town there at that time, because the channel dried out very quickly. There was no longer known. So, Amara West, big channel to the north, big channel to the south. We've got archaeology on each of these channels, so we know they were both flowing at the same time. Also, there's a town at the moment, if you stand in Amara West today, you can't see the river because of the bank of dunes. It doesn't make any sense at all. So the dunes would have been up here on the margins of this channel and not that one. And Amara West was in a rather different environment. But its days were numbered, of course, as soon as those channel systems dried out. So we have evidence for a major contraction around about 1300 BC. And we think that was related to a fall in discharge that resulted from climate change. So let's go further to the south now. This is the northern Dongla Reach, which is more of a sort of geographical survey, looking at a whole series of sites over a much bigger chunk of the Nile Valley. And this was mainly focused on a Kerma age period. This is the city of Kerma to the north, major Bronze Age civilization. But I also show you evidence for Neolithic, Kerma, New Kingdom, and then later periods as well. It's also worth noting that Kerma dominated the Nile Valley here between about 2,500 to 1,500 BC, even up to the Egyptian border. It was a major Bronze Age civilization. This is the Nile at Dongla today, very recently before the Chinese built the bridge. This is the first crossing of the Nile north of Khartoum, and the bridge is now operational. This slide was taken in 2008. This is the northern Dongla Reach. That's Dongla, the town. Up to this point, there was just a single site, archaeological site known here, the site of Kawa. That was a New Kingdom town after the conquest, built in the time of Tutankhamun. Derek Welsby here is a British Museum archaeologist who surveyed this reach in the mid-1990s. This is 80 kilometres north-south. The modern Nile flows on the western side of the valley, and there's a bedrock plateau on here with a series of fossil wadis, and the distance from the channel to this side of the desert here is about 18 kilometres. It's quite a substantial distance. In 93-94, Derek surveyed the central part of the reach and marked on all the archaeological sites with GPS. These include cemeteries, pottery scatters, foundation stones for buildings. It's a very, very rich landscape full of evidence of previous human activity. The following year, 94-95, surveyed to the north, and then we got involved in 95-96. Derek asked Mark Blacksell and myself to come out here. You'll see these sites are not arranged randomly in the landscape, they're aligned with former channels of the Nile. So, one of the challenges then was to understand when these channels were flowing, when they dried out, what the implications were for the archaeology. Now, Isabella Solstrom, Derek Wellesby's wife, is a fantastic ceramicist. She's worked on the pottery from all these sites, and she's been able to characterise each site on the basis of its age. So we can date the channels using the archaeology pretty accurately. But what we wanted to do was come up with an independent age framework for the channel system. So, how do we do that? Now this is standing in the east of the valley floor on the bedrock plateau. There's a Nubian sandstone plateau. This is looking out over a series of alluvial fans. And then there's an old channel system here, which is now being farmed. And the Nile at this point is about 18 kilometres to the west. So it's a flat, fairly featureless landscape, apart from a few dunes and some subtle topography on these paleo channels. Now, we spent a lot of time getting to know the local farmers. Okay, we had great fun doing this, because they were experts in groundwater irrigation. Now their strategy here is they dig pits into the alluvium, they put an Indian diesel pump in the bottom, and they pump groundwater to irrigate these plots, just over a few acres. And these line all the channels, these ancient channels. So we spent a lot of time in these holes. The whole area is filled with, the whole area has these what we call groundwater pump pits. And some of them are 7-8 metres deep, some of them just a few metres deep, but they're providing fabulous three-dimensional sections in the Holocene alluvium, often down to bedrock here, across the whole of the area. So Mark Macklin and I looked down literally hundreds and hundreds of these, logged the sections, sampled them for dating, to build up an idea of when these channels were flowing. We even see bed load from the Nile in some of these channels, classic Nile silts, and then this is the bedrock plateau on the valley floor. So these are the channel systems we've mapped on here. You can see them on satellite imagery. Each of these squares represents a pit that we've logged. We've looked down many more, but these are the ones that we've logged. The ones that are black, we have dates for. We have luminescence dates and a few radiocarbon dates where we found organic material. What kind of sediments do we see? We see Nile bedload, very well-rounded quartzite gravels. We see classic big stacks of Nile silts. And then, closer to the bedrock plateau, we see local wadi sediments, coarse-grained, angular material on alluvial fans that come out in small local wadis. And then, of course, when the channels dry out, they fill up with orange, wind-blown sand. And then, just as we did at Amara West, we also see these channel fills. We get these little flood units buried, integrated with these sands. Now, very simply, we think the Nile records, i.e. the Nile, these Nile silts, they're an indication of a sort of proxy record for global climate, i.e. the intensity of the monsoon. If we've got active wadis, i.e. the local streams, the small streams are flowing, we've got wet climate in the area, so the monsoon is more intense and it's extended further to the north. I'll show you some evidence of that in a moment. So let's think about the early Holocene, the Neolithic Nile, and then look at some of these evidence for wadi floods. And I want to take to the northeast part of this area here, sites 37, 38, 39, 40, got some of the deepest records. We have mapped the paleo channels at this point, but we found some new channels up here. This is a very deep pit. This is classic Nile alluvium, very thick, grey-brown silts. We've got a luminescence date here of 5.5K. One down here of 8.42, that's the oldest state in the area. We've got a big Nile channel lapping up against the bedrock plateau, flowing at this period. So this was early Holocene, more intense monsoon, we think more water coming down the Nile. What's interesting is that the farmers here are farming in alluvium that was deposited in the Neolithic. Okay, so they're farming the alluvium of their forefathers that's over 5,000, 8,000 years old. I'll show you some of these wadis in a moment. One of the things we wanted to do was look at these fan systems. These emanate out of these wadis here. When these were flowing, the local climate must have been wetter. So we were searching, if you like, for a wet Sahara in northern Sudan. So we're looking for the evidence of the African human period in this part of northern Sudan. Now, if you look on Google Earth, these are these wadi systems, these are these beautiful alluvial fans. The grey you see here is ancient Nile silts, and this is what's been farmed by these farmsteads here. Then if you look in more detail, these are some beautiful fans intercalating, coming out of these big wadis here. And I just want to show the record here on pit 37, just on the edge of one of these fans. We've got flood deposits in here, which are wadi floods. Okay, so we know by dating these, this is Mark in the bottom of the hole, we've got bedrock here, we've got a big wadi flood here, coarse bed load, a big wadi flood here, wadi sands in the middle, so the bottom half of this is wadi sediments, and then the Nile came back and we've got Nile alluvium sitting on the top. So these are two big wadi floods. We know that these wadis were flowing at this time, and the date of 5,000 is just at the end of what we might think is the African Humid period. So we can work out when these wadis were flowing. We move to the central part here on this channel we call the Alfreda Nile. We don't get any wadi signals, we just get great big thick stacks of Nile alluvium. And we've dated these to the Kerma period, so again we know this channel is flowing throughout the Kerma period. So by building up these dates, and we've got over 40 dates now across the area, we can work out when these channels were flowing, when they were perennial, when they were seasonal. Just two more concepts. When this channel dried out, the Hawaiian Nile, the Central Nile, in the New Kingdom, the farmers here dug wells. They were tapping into the groundwater there, sort of 1500 BC. And they're beautifully brick-lined wells. These are Nile wood bricks that have been fired. They look like they were laid down there last week, beautifully preserved. This is on an old channel, which now has a big dune. It doesn't look anything like a river channel. But we can excavate the fills from these wells if they fill up, date them, and they give us minimum ages for the switching off of these channels. And these dates actually bring rather well with the archaeology for the termination of that channel. The last context here, just to show you what the geomorphology looks like. This is a channel system here on what we call the Alfreda Nile here, just close to this confluence. This is an old satellite image. This is where this channel joins this one. There's a beautiful convex system here with nice levees. We dug a pit in the bottom. This is the record here. This is what it looks like. Again, we've got orange sands blowing in from, in this case, from the northeast, and we've got these beautiful Ethiopian volcanic silts which represent big floods that reoccupy the channel. But this channel is 18 kilometres from the Nile, and it's about 15 kilometres upstream of where it breaks away from the main Nile. So these were major floods that came down this channel, but with relatively low energy systems. We can sample these and analyse them. So, this gives us this map. We published this in Geology just a couple of years ago. This map integrates a huge amount of information, all the archaeology and all our work on the geomorphology and the sedimentology, which tells us where the channels were flowing, where the channels were seasonal, where the channels were ephemeral. And what we have here in the Neolithic, in the African Humid period, we know all these channels were flowing. The archaeology, some sites are associated with the channels, but many sites are not, because the local climate was wetter. You didn't need to be next to the Nile at this point to subsist and survive in this environment. By the time of the Kerma period, after 2400 BC, some of these channels had dried out. Almost exclusively, every site was associated with the River Nile channel. Because you survived in the desert at this point, the Sahara Desert, as we know it now pretty much, you had to be close to the river. And then we go to the New Kingdom, and then to Kushite, then to medieval. We see a contraction here. This system becomes ephemeral, and then by the time we get to the medieval period, all these channel systems are dry, and all the archaeology is associated with the channel. So we've got a series of contractions here in Kerma period, New Kingdom, then later, and then into the medieval period. Well, falling discharge results in these channel systems drying out. Interestingly, and I won't spend much time on this, we just did a big data analysis of all the available radiocarbon dates and luminescence dates for Egypt and Sudan, most of which come from Sudan. And we did an analysis here to see if we could identify contractions. And this is plots of paleochannels against floodplain. And very quickly, we've got a series of contractions which go back to about 6,000 years ago. So these things aren't just local phenomena. We see these repeatedly at multiple sites in the Nile that suggest there's an overall external control creating these contractions. Okay, there's volume is here, so I'll put something on sediment sources just for the final part of my talk. One of the things that I've done over the years is every time we were down a hole, I took a little sample of sediment associated with each day. So I thought, well, we may be able to do something with sediment and see if there's any changes in sediment sources. And a number of people over the years have tried to work out, study Nile alluvium to see if they can work out what proportion comes from the Blue Nile, what proportion comes from the White Nile, what proportion is windblown dust, etc., etc. And one of the techniques that has been used is something called strontium isotope ratios. So the ratio of strontium 87 to strontium 86. We don't need to worry about that in too much detail, but basically the Blue Nile, sediments coming down the Blue Nile tend to have lower strontium isotope ratios. Sediments coming down the White Nile tend to have higher strontium isotope ratios because these are young volcanic sediments, these are old sediments from ancient shield terrains. And these have been used as a basis to try and separate out the Blue Nile, White Nile contribution, mainly in long course from the delta or from the offshore. So, earlier, this paper published in Nature in 1989, Dan Stanley and Alan Foucault used heavy minerals to try and differentiate between the Blue Nile and the White Nile. It wasn't particularly successful, but they did make the point that because the Nile carries a load derived from markedly different geological terrains, it was expected that mineralogical study of the deposits in the delta would help define changes in paleoclimate. So paleoclimate may influence changes in the tributary contributions. More recently, in the offshore, some French work has suggested the isotopic composition of the sediments for the last 100,000 years can be explained by a simple mixing model between a Libyan Egyptian dust end member and a Blue Nile end member. So the sediments in the Nile offshore for the last 100,000 years are various combinations of Blue Nile or windblown dust. Okay, I want to challenge that and put an alternative suggestion. So these are the data. These are all the luminescence dates that we have in the Donner Reach. These are all the data for strontium isotopes, and we also use another isotope called neodymium, which I'll come to in a moment. So I'll show you some of these data. This is a plot of time going back to 9,000 years ago. This is strontium isotopes here. If we plot the Neolithic samples, so these are samples across the Donner Reach that have been dated to the Neolithic or to the African Human period. And they tend to have strontium isotope ratios that average about 706. Okay? All the samples from the later Kermit period have lower strontium isotopes, which average out here about 0.7055. There isn't actually any overlap between these two groups. So there's a distinctive difference between them. So that's quite a significant change. Then interestingly, if we take the individual flood units from our dry paleo channels and we look at their strontium isotopes, they have much higher isotopes. They plot out up here, even higher than these Neolithic ones. Now, if these were samples from the delta or from the offshore, the traditional explanation of this, well, this may be windblown dust, or the traditional explanation would be, well, these values are higher because they've got more White Nile sediments. Because they're early Holocene, there was more water coming down the White Nile. The White Nile has higher strontium isotope ratios, therefore this must have high White Nile sediments. But it isn't White Nile. That's a result of greater inputs from wadis in the desert Nile. And I'll show you why I think that's the case in a moment. There's another trajectory here. This direction, you've got more windblown dust coming in. So that makes sense. Those flood units in those dry channels are laced with windblown dust. So, what does that mean? Well, it means the end of the African Human period here, wadis are flowing at this point, wadis are not flowing here. The end of the African Human period was very abrupt indeed. And we see a big drop here from these Neolithic samples here in terms of their strontium isotopes above 706. They drop down here to just above 705. There's a major change in the composition of Nile alluvium. And this isn't just a local signal on the valley floor. This is in distances way away from the bedrock plateau. So this is the Green Sahara. This is the Desert Nile. These are contracted channels that have dried out, that have got flood units in, that have also been laced with windblown dust. This also shows, this is for the early Holocene. These data come from various sites across the valley floor. We've got early Holocene ages, and these all show a signal with a very strong wadi component, not just on the margins here. So we think that is real. So what this means is, during the African Human period in the Neolithic, all these channels are flowing, and the wadis are flowing here. So you don't need to be located near a channel. You can get water from these wadi systems. But come the Kermit period, all those wadis have dried out, and the contribution of sediment from this side now is basically dominating windblown sand or windblown dust. So this is the arid Sahara. When I was doing this analysis, it was done, the strontium isotopes was done at the Merck lab in Keyworth by Ian Miller. And he had a PhD student at the time, Laura Fielding from Lancaster, who finished last year. She was working on Miocene and Quaternary deposits in the Nile. She collected lots of wadi samples from various parts of the Nile catchments, and also studied the literature. And these end members here are based on large data sets from various parts of the literature and our own data. Basically what these show is these are mixing curves. This is, if your samples are 100% Blue Nile, Ethiopian basalts, they plot out up here. And then various mixtures at 10% intervals down to North African dust, they plot out down here, it's 100% dust. And these are wadi mud. So I thought it would be useful to plot our samples on here. So if we put the The Neolithic samples, or when we have the Green Sahara, they show a composition which is a mixture of Wadi mud and a mixture of Blue Nile Ethiopian basalts. The Kerma period samples, they plot further up this line, so they've got less Wadi content, they've got more Blue Nile, some of them are sort of 70% here. I'll put the averages on in a moment. And then the Paleochannel fills, which we think are laced with wind, blown dust, they plot on this curve here. So, the Neolithic ones have got 45% Wadi, 55% Blue Nile. Okay, some of those samples here have got even more, down to about 50% here. The Kerma samples, the average is about 60-40 split, 40% Wadi. This is stuff also coming from upstream as well as locally. Some of those samples have got 70% Blue Nile. The modern samples now in the river plot out somewhere up here. And then these units show a 55-45 split between Blue Nile sediments and wind-blown dust. So these are these little flood units we see in these dried out channels. This is the Green Sahara, this is the Desert Nile. So we think this is a good basis to work out that Wadi's made a very important contribution to the sediment over the Nile during the early Holocene and in the mid-Holocene, and they probably do even today. What about the White Nile? Well, the White Nile will plot out down here somewhere. It doesn't plot on these curves. So we can explain the composition of all of these deposits without any contribution at all from the White Nile. Even in the early Holocene, when we know the White Nile had a much higher flood regime, much greater water coming down the Nile. Why is that? Well, the White Nile's got the biggest catchment. If we increase the monsoon and increase equatorial rainfall, Lake Victoria increases in size. The Sud increases in size. This is the biggest wetland in Africa. Becomes a very effective sediment sink. When the Blue Nile's in flood, the White Nile backs up for about 300 kilometres. There's a whole series of physical barriers that prevent sediment leaving the White Nile in a system that has a very low sediment yield in any case. And when we're in flood here, the peak flow to low flow of the Blue Nile is about 40 to 1. Sediment concentration of the Blue Nile can be about 4,000 milligrams per litre. The White Nile just isn't measurable. It's tiny contributions. And this is the time when the floodplains in Egypt and Sudan are inundated. And that's the time when the White Nile doesn't register at all. So we don't see any White Nile signal in any of these records. So what does that mean? It means that the Desert Nile, and we're not just talking about wadis here in northern Sudan, we're talking about wadis in the lower course of the Accra, wadis in the lower course of the Blue Nile, wadis along all these reaches. You'd expect the signal to be cumulative. Some of these big wadi systems here are as big as the Blue Nile itself, and they were flowing and they were perennial. Many of the big wadis here draining the Red Sea Hills would have made important contributions. An interesting idea is that wadi contributions should increase as you go down through Egypt in the early and middle Holocene. So, wadis are important. That's the message. So for the Holocene, particularly the early Holocene, the Nile sediment load is commonly viewed as a three-component system. Effectively, I think we can forget the White Nile in terms of sediment contribution. Wadis are really important during these humid periods, okay? Particularly in the early Holocene. In the Desert Nile, the Ionian contribution is more important. It's a distinctive feature of these Paleochannel fills, but it's also an important contribution to the main Nile. But the Blue Nile and the Accra are always dominant. We're just at different combinations from the different sources. So, wadis are tributaries. It's an Arabic word for a dry river channel, but wadis become tributaries. So this is a fluvial landscape. And during these wet periods, the Desert Nile comes alive, okay? All these river systems would be pretty much permanent, perennial systems with strong seasonal water flows and seasonal sediment yields. Often small mountainous rivers with high sediment yields. So when we go back in time looking at the full Quaternary record and think about these wet periods and the formation of sapropels, we have to factor in a contribution from the Desert Nile, from the wadis in terms of their water and their sediments. So we need to think about these sapropels perhaps right back to the Quaternary in a rather different light. It's not the White Nile, it's the wadis that are important and the Blue Nile at these times. So, some conclusions, okay? Northern Sudan, hope you'll agree, has enormously rich fluvial records that can be dated, and that sets them apart from the records of Egypt, which generally are not dated. And if you want to compare the fluvial records with other records of environmental change and with the archaeology, you have to have robust, independent chronologies. And we've established that for Sudan, but it's yet to happen in most parts of Egypt. The end of the Green Sahara is clearly marked in the fluvial records, and the fluvial record does record a climate signal. Okay? Interestingly, Conventional wisdom was, after the Green Sahara and the establishment of urban civilizations in Egypt, nothing much happened in the climate, probably generally. We also see major episodes of channel network contraction. These happened abruptly, and in terms of your interpretation of the archaeology and the societies on the valley floor, each period, and after each contraction, presented very different challenges for societies subsisting in the Nile Valley at that time. And it was particularly different in Sudan, which was a river of islands. Okay? So it presented very different valley floor environments for the ancient inhabitants. So, the cultural impacts of the major aridification that we know about at the end of the African Humid period, they didn't end at 3,500 BC or whatever. We're dealing with a volatile Nile. Okay? What is in the now desert Nile catchment were major contributors of water and sediment during these humid phases. I think that's important to appreciate. The White Nile sediment contribution was minimal. So, the fluvial archive in the Nile Valley preserves a wonderfully rich and a globally important record of Holocene climate and hydrological change that I think is of significance for our understanding of the deeper Quaternary history of the River Nile. That's a good place to finish. Thank you.
Jamie, that was a splendid and very erudite account, and Jamie's also kindly agreed to answer any questions from the audience. So let me ask if there are any questions to Jamie before we move downstairs. Yes?
When you say the period ended abruptly, are you talking about 10, 15 years or a couple of centuries?
That's a good question. Within the resolution of our dating, what's perhaps a couple of centuries, probably even less than that. I think perhaps the termination of the contractions at Amara West, that probably happened very quickly within the space of a generation. So the end of the African Humid period, maybe a couple of hundred years, maybe more abrupt than that. The resolution of our dating doesn't allow us to be more precise than that.
Chris?
And so what drives the humid pulses? And does it presumably it's what's going on in Ethiopia?
The contractions or
the contractions and
the contractions is an interesting one because there's a fairly well understood mechanism for the end of the African Humid period, which is the precession cycle and various feedbacks in the climate system. We don't have a mechanism yet for these contractions. People are suggesting maybe solar variability that results in a periodically weaker monsoon. There's work that's been done on marine records in the Arabian Sea, and also looking at some of the other fluvial records suggest it could be solar variability. We don't have a mechanism for that yet, but that's one possibility. But I'd be interested to see if anybody's got any suggestions. But we think they're real, and we've put that model out there to be tested. So it'll be interesting to see whether people find those evidence of a step change of a weaker monsoon in other environmental records. But in that part of the world, the lake sediment records aren't particularly good. Most of them have been blown away. So perhaps it's in some of the lakes in Ethiopia. It might be a good place to look.
You were mentioning the importance of wadi flow, and I wondered if you just wanted to comment a bit more about some of those big wadis going off into the desert, like Wadi Hawa. And I mean, there has been a bit of work, particularly for remote sensing data. Do you want to just amplify that a little?
There's been the work in the 1980s done. Stefan Croakland did some work on the Wadi Hawa. They published a paper in Science which established that that channel system was flowing. The data control, in terms of what we can do now, is pretty modest.
Yeah.
So we're really interested to do a full archaeological survey of those big body systems and to date them using luminescence and to look at them in more detail, because I think there's a really important story there. But they're big systems, they're big rivers, and in Egypt now there are big river valleys, and they're big river valleys because they were conveying lots of water at some point in the past.
Yeah.
So, and contributing lots of water and sediment to the main Nile. Yeah. So we're dealing with a radically different system. I gave this talk at the British Museum earlier in the year, and I called it 1,000 Wadis up the Nile, and that kind of captures what we're talking about, 1,000 tributaries up the Nile.
Yeah. Yes.
The sediment cores, I was wondering about the depths of them. It seemed from the scale that you had against some of the slides that you were able to get the 6 great floods of the Nile within a depth of about 3.5 meters. And I wondered if that the maximum depth that you have to take a course.
That slide that we showed, when we dig pits in the middle of those channels, there's a sort of health and safety issue. There's a certain, we went down about 3.5 metres there. And that was, I think that's almost a full record. That just happens to cover a time span of about 1,500 years, something like that. We've got 6 big floods preserved within it. So they were the big floods we think during that time period. One of the other things that we're trying to do with the archaeologists is to link some of those floods with the written records in Egypt of big floods, which is another side to this project, which is quite interesting. But we can only go as deep as we can.
That's interesting. I wondered if you took some course with the boring machines.
No, we didn't do any boring, any augering, because in most places we have these fantastic well holes, and the sections are there for us, and the alluvium is often very, very hard, very strongly indurated. It's almost impossible to dig. Those holes take months to dig. So and you get beautiful three-dimensional sections. So the idea of doing some coring and get some grotty cores that fall out wasn't attractive. But there's a lot of work on coring in Egypt on the floodplain that's wetter.
May I ask you about the early on in the talk you were showing a slide with troughs containing what seemed to be cores. The sapropel?
Yes, that wasn't my data. They were marine cores that have been collected in the Eastern Mediterranean on a big boat with a proper drilling rig. And some of those go about tens of metres down into the Mediterranean sea floor. So
with the dark bands, would that be indicative of mineral material, or is that done to organic material?
Those dark bands are basically very organic rich, which are associated with when the monsoon was more intense and there's more water coming down the Nile. So basically the Eastern Mediterranean had a cap of less saline water on the top. It meant there was less mixing, so you couldn't get oxygen down to the ocean bed, and the organic material didn't break down. So you get these are called the sapropels, sort of stagnation layers, if you like, and they accumulate. So they match up with increases in the discharge of the Nile in periods where we've got greater Nile floods. So they, if you like, they're a very long-term record of changes in Nile flow. But they go right back into the Miocene, extremely long records.
Thank you. What do you think is driving the floods at a sub-millennial, suborbital millennial sort of scale?
Big floods? Don't know. I mean, we think they're big floods, but they could be just floods that, there could have been a blowout in the June, and the floods just went through that time by coincidence. We don't know. We'd like to think that it's a stack of big floods. That's the most sensible option. What's driving those exceptionally big floods? Now, interestingly, those channels in the Mara West, if you take the dunes away, they will flood now during the big floods. So it has to be some mechanism that breaches and breaks through those dune systems. But just a particularly intense monsoon, particularly you've had in recent times, on a warmer period.
But presumably the default is that it's somehow it's monsoon.
Yeah, absolutely. Oh yeah. So big monsoon, big flood. Yeah. These aren't flash floods. These things rise very, very slowly, dealing with huge volumes of water. They spill over into those channels. So there must be a particularly intense monsoon in a particular season that produces a very big flood.
Well, there could be geomorphic reasons.
Quite possibly, yeah. Yes, Bruce.
Very much. When you get into the deeper Quaternary, is it only climatic and hydrological change that's important, or are there other influences such as neotectonic changes, or those sorts of factors?
Well, it's a good question. I mean, most of our work is focused on the Holocene, very recent part of the record. But there is an interesting tectonic history to the Nile that I'm not so familiar with. But so if you're looking at the Blue Nile records, for example, I'm sure there's a tectonic story there. There's a big debate about how long the Nile's been connected to Ethiopia and the Mediterranean, for example. But Tim might know more about that than I do.
Yeah, it used to go to Red Sea at one point.
Yeah.
And so there's the tectonic story in there.
But presumably also linked to the so-called Messinian salinity crisis,
Yeah.
when the Mediterranean dried up and actually carved, the
there's a very spectacular story to the Nile if you go back into the Messinian, when the Mediterranean dried out, so that the Nile cut down into an enormous canyon, much bigger than the Grand Canyon, goes all the way back to Aswan.
Yes.
With huge bedrock cliffs at Cairo and what have you, which is now been filled up. But the Sapropel record, the marine record, which goes back into the Miocene, that indicates that there's been a monsoonal connection between the tropical headwaters and the Nile for at least that period of time.
Okay, thank you. One last question.
So you showed how those branches in the channel have been sort of activated and abandoned and how they contracted and expanded. But the channel system, other than those changes, looks relatively static. Is there any evidence for a natural migration of the channel?
That's a really good question. Now, we've asked that question. When you look at the Dongola Reach, is that those, probably better termed as channel belts, there's probably some lateral movement of channels within those belts. But the archaeology suggests that those belts haven't moved very much. Because you don't build grain stores, you don't invest time building grain stores next to channels if the channels are going to move, they're going to be flooded out. So we've got Neolithic sites, go back 6,000 years ago, and Kerma sites, side by side, in lines along the channels, which would suggest that channel positions are relatively fixed. So the archaeology can help us understand the fact that the channels haven't been that dynamic, and certainly with the broad channel belts. I'm sure there's been changes within them. In the Dongola Reach, what's quite striking is the fixed position of those channels. They haven't moved very much at all. They seem to have, they were going up belly in the early Holocene, and then they contracted and had slowly had less water over the course of the middle Holocene. But there doesn't seem to be any lateral movement because the archaeology would be buried. And we've looked down thousands of holes and we don't see any buried archaeology. The archaeology is still at the surface, so that would suggest the channels are static, which is interesting. Very rare to see any archaeology at all in any of those holes we looked down hundreds of.
Well, we may do work hard for an hour and a bit now, so I'd like to invite everybody to go down and share a glass of wine or a drink downstairs at the reception. Before we do that, Jamie, you've taken us on a formidable tour involving dramatic field terrain, high quality lab work, and really to address the question of how dramatic global changes can occur over human timescales. So we're looking at some of the biggest climate changes that we can envisage that affected societies, which were ancestral to our own, the ancient Egyptians and Nubians and so forth. So I think it's been a splendid occasion. Thank you very much indeed. Can you join with us in thanking Jamie for his talk?